solubility equilibria. An example of that, let's take aluminum chloride, and that's extremely soluble. So I've drawn a much bigger arrow in the direction of forming the two aqueous ions, the aluminum 3 ion and the chloride ions. Okay, it's very soluble. So that means its solubility product, or its equilibrium constant for solubilization, is much, much greater than 1. And then on the other hand, we have aluminum hydroxide. Okay, aluminum hydroxide has a much smaller arrow going in the solubilization direction than it does in the direction of forming an insoluble precipitate, and that means that it is insoluble, and its KSP is much, much, much less than 1. In fact, its KSP is equal to 2 times 10 to the minus 33rd power. Okay, so you might be asked, well, how much aluminum 3 would form if I put some aluminum hydroxide in a beaker of water? What would the concentration of that aluminum 3 ion be? Well, I need to think about what the KSP is in terms of these species, soluble aqueous species. Okay, so that's an aluminum 3, and then I have these hydroxides. Okay, and we know that's equal to 2 times 10 to the minus 33rd power. And so if I was trying to figure out how much, what concentration of aluminum 3 is produced when AlOH3 is dissolved in water, or attempted to be dissolved in water, well, you need to create an algebraic equation that relates to stoichiometry. So KSP is going to equal to, say, some concentration of X concentration of aluminum 3. And then for the hydroxide, remember, you get 3 hydroxides per aluminum, so it's 3 times X to the 3rd power. That's going to be equal to 27X to the 4th power, okay? And so then X will be the 4th root. This is where the calculator will come in handy. I don't expect you to be able to do that in your head. Just the square root of the square root. And that will give you about 3 times 10 to the minus 9 molar. Okay, not very much aluminum will go into solution. Now, the wrinkle on this question would be the following. What if I added a little bit of sodium hydroxide? Would more or less aluminum be in solution? If I added a little bit of sodium hydroxide to this, just, say, I don't know, 100 millimolar. Much, much less, okay? Much, much less, that's right. Because it's going to be to the cubed power effect there. All right. We also talked about acid-base equilibria a lot, and I'm not going to do this justice. I recommend reviewing it, though. Acid-base equilibria, and here's a general acid, HA, okay, and it can dissociate to A minus and H plus, okay, and so there's an acid dissociation. We call it Ka. That does not mean dissociation. It means acid dissociation. Acid doesn't mean association. Acid dissociation, and that is equal to concentration of A minus and H plus over HA, okay. And another way of writing this out, and I'm not going to go through all the algebra to get to this, is we can write out the Henderson-Hasselbalch equation, which is a very useful form. You can plot then the concentration. Let's say we're going to do a graph here of, and on this action we'll plot the fraction of the acid in the protonated form. So fraction can go from 0 to 1, because remember that HA plus A minus is going to be some constant, okay? And so all of your, and if we plotted this versus pH, and let's imagine our pKa here is something around 5. That's good. I kind of caused a problem, but so at 5, so we know at low pHs, of course, you're going to be fully protonated, the acid will be protonated. When you hit the pKa, then A minus and H plus are going to be equal concentration. The log terms going to become 0. pH is going to be equal to pKa. So I put a dot right there. The only point where A minus can equal HA is when the fraction of HA is 0.5. 0.5 divided by 0.5, we can do this in terms of fractions, is going to be equal to 1. The log of that 0. All right. Now, you might ask, well, what's going to happen at pH 4? Well, at pH 4, we have 1 log unit. We're 1 log unit away from the pKa. So that would mean that there's a factor of 10 difference between A minus and HA. And, obviously there's going to be more HA at lower pHs. So it'll turn out that'll be like 91.9 actually. And then it'll be the opposite there. It'll be about 90% at pH 6. This is 50-50. This is, say, 10-90. And this is 90-10 of HA to A minus. HA to A minus. Okay? So another question would be, if you had acetic acid, let's say this is acetic acid, pK is a little high, but that's okay, and you had some acetic acid you're titrating with sodium hydroxide, would you rather use phenolphthalein as an indicator for the end point of the titration? That has a pH range, call it 8 to 9 or so. You don't want to use that. I didn't tell you the other option. Let me tell you the other option. Okay. The other option is methyl orange. Methyl orange, let's say, has a pK around, 4 or 5, has a good range in there, around pH 4 to 5. Would you rather use methyl orange or phenolphthalein to measure the end point? You're starting with the acid, you're titrating in sodium hydroxide. No, you want to use phenolphthalein for the end point, because you want something that changes over. Your phenolphthalein is going to be changing over down here, okay? Something like that. So you want something that's going to signify the end point of the reaction. But if you're talking about methyl orange, you might be seeing color changes in here from, whatever. Try to get my yellow here, from yellow or whatever it is to that dark orange color. That would be near the point where your pKa is equal to pH. That's not the end point. The end point of the titration is after all the acid has been completely deprotonated. So you want to go for the phenolphthalein in the 2 choices I gave you. Okay. So check that out. I know that was tricky what I was asking you based on the graph that you had here, but it was a lot of fun. All right, so calorimetry, you made biodiesel. That was exciting. Biodiesel. Yes, phenolphthalein is the best. And you took trilinolein from soybean oil. It's a triglyceride. You added 3 methanols, and you made 3 methyl linoleates plus 1 glycerol. Okay, now how did you catalyze that reaction? What did you add? What was your catalyst? What did you guys use sodium? Hydroxide or potassium? Potassium? Okay. Whatever. I'll put an or there. Use either. And you produced this guy. 3, 4. Oh, shoot. That's a bad drawing. Okay. Yeah. I'm annoyed by my hastiness there. I think that's right, methyl linoleate. So what is this compound? It's an ester. It's an ester, right? It's an ester. It's biodiesel. There's a lot of things that it is. Here's your ester. Sorry, it's not a good question. All right, and you have this reaction, because we're talking about calorimetry here, believe it or not. This is what kind of reaction did I draw here? Combustion, right? Combustion reaction. And how hot is this going to get? Well, this is going to get pretty warm when you burn a kilogram of this. It's going to liberate 37 megajoules per kilogram. Okay? So, let's do a fun problem. Let's imagine we had a 10-liter calorimeter. The calorimeter is water filled. Okay, there's no calorimeter constant in this particular exercise. And we burned 100 grams of biodiesel. So what is a delta T? How do we figure that out? Well, first of all, you need to figure out exactly what Q will be, because we need to think about satisfying this equation. We need to think about Q equals M Cp delta T. And so we know the heat capacity of water is 4.184 joules per gram per degree C. We know the mass of water in this particular calorimeter is 10,000 grams. And we know delta T's are unknown. So you say, well, how are we going to get Q? Well, that's pretty straightforward. We're going to use the heat of combustion, which is 37.3 times 10 to the 6 joules per kilogram. And we're just going to factor label that. We did only 100 grams. We burned only 100 grams. There's 1,000 grams per kilogram. So that'll give us 37.3 times 10 to the 5th joules. Okay. And now we can just plug and chug that into our equation there. So delta T is equal to 37.3 times 10 to the 5th joules. And we'll have 10,000 grams of water. And we'll have, this is our degree Celsius gram for our joule per degree Celsius per gram written upside down. Because remember, I want to cancel my joules out, I'm going to cancel my grams out, and be left with 88.9 degrees C. Okay, that's pretty warm. I'd have a pretty big calorimeter, 10 liters to capture that heat from that biodiesel. I don't think you guys are burning quite that much. You're burning a few grams, so you could use a much smaller calorimeter to capture the heat. Okay, so that's just a fun example there. I don't know how much time we have left here. We'll try to hit the last page here. So interactions with light. We did this most recently, and ultimately, you should understand how to use Beer's law. That's very important. You'll definitely have something on there about Beer's law. And you're going to have to think about molecular orbitals and why do molecules absorb light in the UV visible region? And what are the rules? So, when we have a molecule like ethylene, we have, in this ethylene, we have a pi bond, okay? So the original p orbitals have some energy here, okay? And when they formed a pi bond, it was lower in energy, okay? There are 2 electrons in that pi bond. They reside down here. Now, there's also an antibond up here. That's higher in energy, okay? We call that pi star, and that's an antibond. We thought about what does that look like? Well, an antibond is going to look something like this. The orbitals are out of phase with one another, and they're bifurcated. There's a node. There's a node here, and to draw phase, I'll shade. These are oppositely phased. They're destructively interfering with one another. There's a high energy situation, much higher energy than this situation, where we have constructive, in-phase overlap of the p orbitals, okay? Those electrons are nicely spread out now. They're happy. They're not in a high energy situation. This bonding here is more stable than the original p orbitals, okay? So that's your pi bond. And there's a key thing to consider, this energy here, this energy gap. Because there's an amount of energy, if we had a big photon come in, and photon came in, and it could excite this electron, say, an electron could go up, okay? But to go that distance, to go into that anti-bonding orbital during excitation, it's going to have to go this energy gap, okay? So you need to think about some relationship between energy and frequency of light. You have this relationship between wavelength and frequency. So you can write out energy equals Planck's constant times frequency, speed of light equals wavelength times frequency, and then you can write out energy equals Planck's constant speed of light over wavelength. You see there's an inverse, this is an inverse relationship, okay? So bigger wavelengths for max absorbance for your molecular system correspond to small energy gaps, okay? And you get smaller and smaller energy gaps when you make bigger and bigger conjugated pi networks. We talked about basically conjugated pi network as being, double bond, single bond, double bond, single bond pattern. So that's why beta carotene is this really long molecule. In order to be orange and absorb strongly into blue and cyan and green and look orange, that molecule needs a pretty extensive conjugated pi system and a correspondingly smaller energy gap than ethylene here, which is going to absorb way down in the UV. It's going to have a big energy gap. So the key thing to remember is on the blue end, on the purple end, on the ultraviolet end, that's a big energy gap, much smaller pi conjugated network. And on the red end, approaching the infrared, if you're absorbing photons way down there, then you're a very, very large pi conjugate system with a very small energy gap. We talked about that, and I also gave a clicker question. You should review that. The other kinds of electrons that can be excited up to pi star are the non-bonding electrons. You find those in oxygens and nitrogens and halogens. So you could end up with a much different band gap there because that transition is a smaller energy transition than the pi star. So that is going to be it, unfortunately. But you can send me an email if you have an emergency question, and I'll try to get to your email questions before exam. And I'd appreciate one last thing that you'd fill out if you can. It's online. The course evaluation. It's useful to the university and to me. Okay. Good luck on your exam.